Hey everyone, Mr. Hauk here. Alright, so today we're going to be looking at the 9.7 Polar Calculus Day 2 notes. So in the previous set of notes, 9.6, we actually didn't really do any calculus, so today's actually going to be kind of the first day of polar stuff with calculus as well. Alright, before we get started though, we have to have a very quick review of pre-cal. So in pre-cal, whether you took AP pre-cal or whether you took accelerated pre-cal, you should have some experience converting between rectangular and polar coordinates. Okay, so let's say that you have polar coordinates r and theta. If you want to convert from r and theta into rectangular coordinates x and y, we would use these two equations right here, where the x coordinate would be r times the cosine of theta, and the y coordinate would be r times the sine of theta. Let's say that you had x and y, and you want to convert them into r and theta, then we would use this set of equations. Now, more specifically, this r squared equals x squared plus y squared, we would want r by itself, so we would take the square root of both sides. So we'd really use this. R equals plus minus the square root of x squared plus y squared, okay? And then to find theta, we would do tangent of theta equals y over x, and we'd find all the thetas such that the tangent value is whatever y over x is. Okay? Notice, by the way, this is going to play an important role when we start taking derivatives, that when we do this, when we represent x as r times cosine theta and y as r times sine of theta, this represents x in terms of theta and y in terms of theta, which actually creates parametric equations. Just instead of t, we're using theta. All right, so let's do a couple quick conversion problems, and then we'll start introducing some calculus. So example 1a, we want to convert the polar coordinates 2, 5 pi over 6 into rectangular coordinates. 2 is r, 5 pi over 6 is theta. So we want to convert r and theta into x and y. We know x is r times the cosine of theta. In this example, r is 2 times the cosine of 5 pi over 6. Cosine of 5 pi over 6 is negative root 3 over 2. So 2 times negative root 3 over 2. The 2's cancel. We get negative root 3. To get our y coordinate, we would do r times the sine of theta. Again, r is 2. Sine of 5 pi over 6. Sine of 5 pi over 6 is 1/2. 2 times 1/2 is simply 1. So our x and y coordinates would be negative root 3, 1. Okay, so that's converting polar into rectangular. Example 1b is going to convert rectangular into polar. So this is our x, this is our y. We want to convert into r and theta. So r is going to be plus minus the square root of x squared plus y squared. X is 3, y is negative 3. All right, 3 squared is 9, negative 3 squared is 9, 9 plus 9 is 18, and the square root of 18 is 3 root 2. So we have r is plus minus 3 root 2. Then we have tangent of theta equals y over x, negative 3 over 3. Negative 3 over 3 is negative 1. So we want to find theta, and theta is going to be all the angles where the tangent values are negative 1. The tangent values are negative 1 at 3 pi over 4 and 7 pi over 4. Now, we have to be careful here. We have to be very careful with polar. The point 3, negative 3, if you think about 3, negative 3, if you were graphing it, 3, negative 3 would be in quadrant 4. So we must take 7 pi over 4 as our angle. That's a quadrant 4 angle. 3 pi over 4 is in quadrant 2. So our polar coordinates we would take the positive r value, 3 root 2, and the angle 7 pi over 4. Okay. Now, if you remember from the previous set of notes, you could also have, we talked about if you change your r value to be negative, you can add or subtract pi. We wouldn't add pi because that would put you over 2 pi. If we subtracted pi from 7 pi over 4, so 7 pi over 4 minus 4 pi over 4, you would get this coordinate right here. I prefer to use the coordinate that has the positive r, so I would use this one. All right, so that's just a small little recap of converting polar and rectangular coordinates from pre-calculus. All right, now what we want to do is we want to start applying calculus things. We want to start taking derivatives. We're going to be finding area enclosed and things like that, and we'll get to all that soon. All right, but the important thing here to start off with is, again, realizing that we can represent x and y in terms of theta. Okay, so we have parametric equations for x and y. That means, and I actually want you to ignore this, I'm going to show you what I do instead. What that means, if you're asked to find the derivative dy dx, if you're asked to find the slope dy dx of a polar graph, of a polar curve, then just like with parametric equations, like dy dx, we would have said dy dt over dx dt. For polar, dy dx is going to be dy d theta over dx d theta, where y is r times the sine of theta, and x is r times the cosine of theta. I want this to be a flashcard. All right, I want that to be a flashcard. All right, so let's see an example. This is actually a pretty lengthy example. Try to write relatively small. We're going to fill a lot of the space in. So example 2, find dy dx of the graph of the polar curve r equals 2 plus 2 sine theta at theta equals pi over 2. Then write the equation of the tangent line at theta equals pi over 2. So ultimately, we're trying to write the equation of the tangent line. Okay? Ultimately, we're trying to write the equation of the tangent line. This means we need to know the slope, dy dx, when theta is pi over 2, and we need to know an x and a y coordinate when theta equals pi over 2. So I'm actually going to work on that part first. The very first thing we need, though, is we need x and y in terms of theta. So let's go ahead and do that. X is r times cosine of theta. R in this example is 2 plus 2 sine theta. Distribute the cosine of theta. Okay, and let's go ahead and find x when theta equals pi over 2. So when theta equals pi over 2, we have 2 cosine pi over 2 plus 2 sine pi over 2 times cosine pi over 2. All right, well, the cosine of pi over 2 is 0. So that's 0, that's 0. 0 times this is going to make the whole thing 0. So when theta equals pi over 2, x is going to equal 0. Okay? Now let's go ahead and get y. We know y in terms of theta. Y is r times the sine of theta. A little bit right here, separator work. R again is 2 plus 2 sine theta. That was given to us. We're multiplying this by sine of theta. Go ahead and distribute your sine. This is going to be 2 sine of theta plus 2 sine of theta squared. Sine of theta times sine of theta squared. And let's go ahead and get y evaluated when theta equals pi over 2. All right, so we're going to have 2 sine pi over 2 plus 2 sine pi over 2 squared. Sine of pi over 2 is 1. 2 times 1 is 2. Sine of pi over 2 is 1. 1 squared is 1 times 2 is 2. So this gives us 4. All right, so y when theta equals pi over 2 is equal to 4. All right. Now let's go ahead and calculate dy dx, the slope. Dy dx equals dy d theta over dx d theta. This equals, all right, so on top, we're taking the derivative of y with respect to theta. All right, so here is y in terms of theta. Let's take that derivative. Derivative of 2 sine is 2 cosine plus, here we're going to have to apply power rule with chain rule. 2 times 2 is 4. Inside sine of theta, multiplied by the derivative of the inside, which would be cosine of theta. All right, so 2 cosine of theta plus 4 sine theta cosine theta. Now we do dx d theta. All right, so here's x in terms of theta. Let's take its derivative. Derivative of 2 cosine is negative 2 sine plus, and then here we're going to have to do product rule. 2 sine of theta times derivative of this, derivative of, what was that again? Cosine is negative sine, plus cosine times the derivative of that. Derivative of 2 sine of theta is just 2 cosine theta. Needed a little bit more space. All right. Okay, so you can clean this up a little bit if you want. Let's clean this up real quick. So on top, 2 cosine theta plus 4 sine theta cosine theta. On the bottom, negative 2 sine theta minus 2 sine of theta squared plus 2 cosine of theta squared. All right, now we want to find dy dx such that theta equals pi over 2. This is going to be our slope at theta equals pi over 2. All right. Well, if I plug in a pi over 2, cosine of pi over 2 is 0. Sine of pi, so we got 4 times sine of pi over 2 is 1, but then cosine of pi over 2 is 0 again. So the whole top is 0. On the bottom, negative 2 times, well, sine of pi over 2 is 1, so we got negative 2 times 1 minus 2. Sine of theta is 1, 1 squared, that's times 1. Cosine of pi over 2, that's going to be 0. So our slope, 0 over negative 4, which is 0. Okay, so now we have all the pieces we need to make the tangent line equation. We have our x1, y1, and we have our slope when theta equals pi over 2. So y minus y1 equals m, x minus x1. y1 was 4. Slope is 0. x1 is 0. Y minus 4 equals 0. Or y equals 4. All right, a lot of work, but that's how you would handle a problem like that. All right, example 3. Find points r comma theta of horizontal and vertical tangency. Okay, so let's look at these individually. Horizontal tangency means dy dx, which is dy d theta over dx d theta. If it's horizontal tangency, this would be 0 over some number. So horizontal tangency means dy d theta equals 0. Vertical tangency means this dy dx, which again is dy d theta over dx d theta. Vertical tangency means this is equal to some number over 0. So basically, horizontal tangency, the top dy d theta equals 0. Vertical tangency, the bottom dx d theta equals 0. Okay? That means we need to find dy d theta and dx d theta and set them both equal to 0. But to find dy d theta and dx d theta, we need to have x and y in terms of theta. So let's do that real quick. X is r times cosine theta. R in this example is 2 cosine theta. So 2 cosine theta times cosine theta. That's 2 cosine of theta squared. Okay. Now let's get y. Y equals r times sine of theta. That's going to be 2 cosine of theta times sine of theta, which you can't really simplify, just 2 cosine theta sine theta. All right, not a lot to do there. All right, let's go ahead and actually, let's get their derivatives real quick, because we're going to need those. Dx d theta, this is going to be power rule with chain rule. 2 times 2, 4. Cosine of theta times the derivative of the inside, negative sine of theta. So this is negative 4 cosine theta sine theta. All right, dy d theta is going to be product rule. 2 cosine theta times derivative of sine, which is cosine, plus sine theta times derivative of 2 cosine theta. So dy d theta is going to be 2 cosine of theta squared minus 2 sine of theta squared. All right. So horizontal tangency, let's handle that one first. We want dy d theta equals 0. This means 2 times cosine of theta squared minus 2 times sine of theta squared equals 0. Okay, when I look at this, here's what I see. Let's go ahead and I'm going to add the 2 sine of theta squared to the other side. That equals 0. All right. Then I'm going to divide both sides by 2 cosine of theta squared. So on the left side, we get a 1. On the right side, 2's cancel. Sine theta squared divided by cosine of theta squared is tangent squared. Okay, take the square root of both sides. When you take the square root of 1, you're going to get plus or minus square root of 1, so plus or minus 1. And we need to find all the angles where the tangent is positive or negative 1. This is going to be all the pi over 4s. But notice, by the way, that we're restricted between 0 and pi. So really, just pi over 4 and 3 pi over 4. All right. So that's for horizontal tangency. For vertical tangency, now we're going to take dx d theta and set that equal to 0. All right, so dx d theta we found to be -4 cosine theta sine theta. Set this equal to 0. Divide both sides by -4. Okay, and basically this is going to be find all angles where either sine or cosine is equal to 0, between 0 and pi, not including pi. Again, notice that the pi does not have the equal to sign. So 0 to pi, not including pi, where either sine or cosine is 0. So cosine could be 0 at 0. Sine could be 0 at pi over 2. All right. Okay, next, arc length of polar curves. Arc length of polar curves. I have not seen this really show up, but I want us to memorize it and have a flashcard of it just in case. Again, I haven't really seen this show up on the AP exam, but we want to be careful. All right. So the length of a curve with the polar equation r equals f of theta over the interval alpha to beta. So this is the Greek letter alpha, Greek letter beta. So we have some angle, our angles between alpha and beta. This is how we calculate the arc length of a polar curve. It's the integral from alpha to beta, square root of r squared plus dr d theta squared d theta. Okay. The first one is calculator active, so use your calculator to calculate. But let's find the length of the curve when we know r is 2 minus 2 cosine of theta over the interval from 0 to 2 pi. All right, so that's going to be the integral from 0 to 2 pi, square root r squared, r is 2 minus 2 cosine theta, so 2 minus 2 cosine of theta squared, plus dr d theta squared. Okay, so we need to calculate dr d theta, so we're just going to calculate r with respect to theta, and that would just be 2 sine of theta squared d theta. Go ahead and throw that in the calculator, double check that you get the answer that I get. Okay, so pause the video if you want to try it out, double check that you get 16. All right, example 5. Let's do a quick one by hand. This one turns out to simplify pretty nicely. So find the length of the curve when r is equal to 2 cosine of theta over the interval negative pi over 2 to pi over 2. So we have the integral negative pi over 2 to pi over 2 square root. Let me actually make this a little smaller because I might need a little bit of space here. So integral negative pi over 2 to pi over 2 square root. All right, first thing is r squared, so we have 2 cosine of theta squared plus dr d theta squared, so that's going to be negative 2 sine of theta squared d theta. Let's simplify this. That's a terrible integral. Hold on. All right, so this is going to be 4, so 2 cosine of theta squared. 2 cosine of theta times 2 cosine of theta. That's 4 cosine of theta squared. Negative 2 sine of theta times negative 2 sine of theta is 4 sine of theta squared. Continuing to simplify. Let's factor out the 4. Cosine squared plus sine squared is equal to 1. Square root of 4 is equal to 2. All right, so now we have a really, really easy integral to take. Antiderivative of 2 with respect to theta is simply 2 theta, evaluating from negative pi over 2 to positive pi over 2. So this is going to be 2 times pi over 2, that's evaluating at the upper bound, minus 2 times negative pi over 2, evaluating at the lower bound, subtracting them. So pi minus negative pi, so pi plus pi, which is 2 pi. Nice and easy arc length to evaluate, because a lot of the simplification there. All right, here's one of the really big topics from Unit 9 that gets tested on the AP exam, polar area. Again, I haven't seen polar arc length get tested that much. Polar area, you're guaranteed to get tested on. So we're going to be looking at areas enclosed by polar curves, not under. Okay, these work a little differently than rectangular coordinates. We're not looking at area under a curve. We're looking at area enclosed. Okay, enclosed, not under. Very important. The formula for polar area is different from all our previous area formulas because it's not based on rectangles. It's based off of sectors. Okay, it's based off of sectors. Polar area uses an infinite number of infinitely small sectors to add them together and find the area. Remember that a sector of a circle is like a slice of a pizza. Okay? And I believe when you took geometry, you looked at areas of sectors. Okay? So the area of a sector of a circle is 1/2 theta r squared, where theta is measured in radians. And let's say that our sector here is going from alpha to beta. Okay? And here's our polar curve. The idea is we want to look at the area of a small sector. So let's say we were looking at a sector here. Okay, let's say we had this really small sector. Okay, well, the area of a small sector we know the area formula is 1/2 theta times r squared. But the thing is, theta is getting infinitely small. We want to add an infinite number of these small sectors together. So instead of theta, when we think about infinitely small thetas, that's going to be our d theta. Okay, so this is now going to be 1/2 r squared d theta for a single really small sector. So the area of infinitely many of them, when I add them all together, is going to be the integral from alpha to beta 1/2 r squared d theta. Flashcard. You don't need to put the infinitely many part there, but basically this is going to be area enclosed for polar curves. Flashcard. So one side, area enclosed, then this integral right here on the other side. Integral from alpha to beta, 1/2 r squared d theta. All right, so let's try a quick example here. Find the area bounded by the graph of r equals 2 sine of theta. Note, by the way, that that follows the format of a circle. This is a circle. Diameter 2, which means radius 1. Okay, so If you're being clever about it, if you understand that's a circle of diameter 2, well then the area of that circle is simply, we know the area of a circle is pi r squared. Your radius is just 1. So the answer we get should be pi. Okay? Let's verify that by actually setting up the integral the correct way. So if I wanted to do this, the area enclosed by the circle would be the integral from 0 to pi. Notice, by the way, we're going 0 to pi, not 0 to 2 pi, because in the previous set of notes, for a circle, we only had to go from 0 to pi to produce the graph once. If you go 0 to 2 pi, it's going to double it. We don't want to do that. Okay, so for a circle, we're just going 0 to pi. 0 to pi, 1/2 r squared, r is 2 sine of theta, so 2 sine of theta squared, d theta. All right. 0 to pi, 1/2, 2 sine of theta squared. And this, by the way, go ahead and use your calculator actually to calculate this. Yeah, let's go ahead and use your calculator to calculate this, just for the sake of time. You're going to see that you get pi. All right. Let's do some that are a little bit more interesting, though. All right, example 6, calculator active. Find the area bounded by the graph of r equals 2 plus 2 cosine of theta. All right, 2 plus 2 cosine of theta. I cannot leave the screen to go to a different calculator, or this, it'll stop recording, unfortunately. So let's go ahead. Let's do a little makeshift picture. If you were to graph r equals 2 plus 2 cosine theta in your graphing calculator, while your calculator is set to polar, you would get a graph that looks a little something like this. I do my best to imitate this. Probably going to do a pretty bad job, though. Yeah, pretty bad. Let's try that one more time. Something like that, sure. Okay. Now the point is, to get the whole graph to generate, and using your knowledge of your different polar curves, we would have to go all the way from 0 to 2 pi. Okay? So the area bounded by this graph would be the integral from 0 to 2 pi. You need to go from 0 to 2 pi to generate the whole graph. 1/2 r squared, r is 2 plus 2 cosine theta, d theta. Now you have the option to pull the 1/2 outside if you want to. Doesn't really matter. It's calculator active anyway. Go ahead and throw this into the calculator and make sure that you get the answer that I have. All right, so again, I encourage you to pause it, try it on your own, make sure you get 18.850. All right. Now let's look at the rose curve. For example 7, the rose curve r equals 2 sine of 3 theta. I usually like to have this part in parentheses right there, 2 sine of 3 theta. And notice it says find the area of one single petal. Okay? One single petal. So let's get a visual real quick. Again, I can't leave this screen, but it would look a little something like this. That's pretty bad. Something like that. Okay? It would look a little something like that. But notice that it says just one petal. So one of the things we saw yesterday on the 9.6 set of notes, if we take our curve, in this case r equals 2 sine of theta, if we find out where the curve hits the pole, okay, so where curve hits the pole. Let's go ahead and do that real quick. So we would take 2 sine of 3 theta, set it equal to 0, okay, because we hit the pole when r is equal to 0. Let's divide 2 on both sides. Sine of 3 theta equals 0. We know sine of theta equals 0 at 0, pi, and 2 pi, and so on and so forth, right? So 3 theta is equal to 0, pi, 2 pi, 3 pi, 4 pi, dot, dot, dot. Divide all those by 3. 0, pi over 3, 2 pi over 3, pi, 4 pi over 3, dot, dot, dot. And what we saw yesterday is if we look at any two of these that are sequential, any two that are next to each other, like these two right here, these two would make one petal. Okay, that's going to allow us to go ahead and calculate the area of one petal. So the area of one petal is going to be the integral from, now we pick any two that are next to each other. I'm going to go 0 to pi over 3. 1/2 r is 2 sine 3 theta squared d theta. So 1/2 2 sine of 3 theta squared d theta. Take a moment, plug that into the calculator. Make sure that you get the answer that I get. Very important that you plug it in the calculator and check yourself that you get the correct answer. All right. Number 8. Not calculator active, but it just says to write an integral expression, so we're not solving. Write an integral expression that represents the area of one petal of r equals 4 cosine of 2 theta. Okay, so same deal. We're looking for a petal, the area of a single petal. So let's go ahead and find out where our curve hits the pole. 4 cosine of 2 theta equals 0. This means cosine of 2 theta equals 0. Divide both sides by 4. Cosine is equal to 0 at pi over 2 and 3 pi over 2, all the odd pi over 2s. So that means 2 theta is equal to pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, dot, 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 right? Divide all those by 2 to get theta by itself. We got pi over 4, 3 pi over 4, 5 pi over 4, dot, dot, dot. And remember, we only need 2 of them that are next to each other, 2 sequential angles, to generate one petal. So I just usually take the first 2. So an integral expression that could help us find the area of one petal, we could say integral pi over 4 to 3 pi over 4, 1/2 function r squared, so 4 cosine 2 theta squared d theta. And this is not the only correct answer, but this is one of them. We could have, instead of going from pi over 4 to 3 pi over 4, we could have done 3 pi over 4 to 5 pi over 4, because these two, again, are sequential. They're next to each other. Okay? So either way, either would have worked. All right, final problem. Find the area inside one loop. Okay, area inside one loop. So same deal, one loop, we want to take our function, and we want to find out when r equals 0. Okay? So 4 cosine 2 theta equals 0. Is that the same thing here? Yeah. So we're going to get the same angles. Dot, dot, dot. Same work as we just did right here. We're going to get pi over 4, 3 pi over 4, 5 pi over 4. and so on. Again, any two that are next to each other, this will give us a loop. All right, let's go ahead and try to calculate. So our area is going to be the integral from pi over 4 to 3 pi over 4. 1/2. Now here's the tricky part. Don't be caught off guard by this. This is r squared already. So we're not going to square this, okay? We're not going to square this. That already is r squared. So 1/2 4 cosine of 2 theta d theta. Again, this part already is r squared. All right, simplifying this, pi over 4 to 3 pi over 4. 1/2 times 4 is 2. We get 2 cosine 2 theta d theta. Take the antiderivative of 2 cosine 2 theta. That's going to be 2 sine of 2 theta times 1/2, okay, because of that 2 on the inside. You can do the u sub if you want to, from pi over 4 to 3 pi over 4. 2 times 1/2, they cancel. We got sine of 2 theta from pi over 4 to 3 pi over 4. And now let's evaluate. So upper bound, 2 times 3 pi over 4, that's just simply 3 pi over 2. So sine of 3 pi over 2. Minus, plug in your lower bound. 2 times pi over 4 is just pi over 2. Sine of 3 pi over 2 is -1. Sine of pi over 2 is +1. And we get -2. All right, y'all. Hopefully this video has been helpful. I will catch y'all.